Hi everyone. I'm gonna use costs, objectives, rewards somewhat interchangeably in this talk. So I tend to work on, I don't know why this isn't working. I tend to work on human-robot interaction, so the algorithm, how algorithms for robotics need to change when you get robots to work with and around people. So we work on collaborating with humans and quad orders navigating around humans and autonomous cars being able to do their job in the presence of human drivers and things like that. And I bet that that's what Steve and Ben thought I would talk about when they invited me to come in this workshop. But instead, I wanted to share with you something that I found over the years to be even more fundamental problem than the interaction with people. And it comes from a bottleneck that I keep running into, sort of a roadblock I keep running into whenever I try to get robots that interact with people. And that is setting the robot's objectives, setting the reward function to begin with. And so Ross Stedrick talked this morning about the onion problem, and this is kind of my own version of the onion problem. So he talked about, imagine you want a robot to chop an onion. That would be hard because, you know, what's the state and so on and so forth. And then he kind of went to the board and developed sort of a formalization of the onion problem. And I took a picture of it, and I want to point something out. He defined an objective. So first of all, it became the carrot problem because he explained, you know, onions are hard to deal with. Cool. But then there's this thing that showed up, right? Which is the objective was to move pieces to a target set. And he kind of had to do that because if I step back and think about how would I code up the objective to be chop the onion, I'd have a pretty hard time because I don't know, what does it mean to chop an onion? How do I turn that into math that I can write down as a cost function for the robot to optimize? That sounds pretty hard, right? Let me give you my own version of that kind of onion problem. I don't work on getting robots to chop onions, but I work on autonomous cars, for instance. I've been doing that for the past few years. And when I got into the autonomous car area, I was focusing on interaction with people, right? How do you get these cars to coordinate with people? And I thought, well, that's going to be the really hard part because it involves being able to anticipate human behavior and so on. And it is really hard. But I thought sort of mistakenly that writing down the cost function for an autonomous car would kind of be the easy part, right? Because like what is there? Like you kind of want it to drive and not crash and get to its destination. And that's sort of what we started off with. We said, okay, well, the car probably has some sort of route, so I should put a term in the objective in the cost function about following that route, making progress along that route. Then the car needs to obey traffic rules, right? So it kind of has to stay on the road and drive in its lane, not in between lanes and all that, not cross double yellow lines. Have to put things like that as part of the cost function as well. And then there's other people around, like human-driven vehicles, pedestrians, and so on, and you don't want to hit those. So there has to be something in the cost function about that. So that's what we started with. We said, I'm going to create a cost, and you can use soft costs or constraints or whatever. It's sort of not quite the point here, but the bottom line is you create something that measures some notion of safety, efficiency, and sort of law abidance, and you figure out how to combine them, and you go. And the car optimizes that. But it's a trajectory psi that is optimal with respect to this cost function. And usually what we do is model predictive control. We take one step along this trajectory. The world changes around us. We replan. Okay, so this, we tried it out in a few different scenarios. So here the car is kind of way in front of the person. And this is the beauty of optimization. It kind of figures out the right thing to do. Here it merges in front of the person and lets the person has enough space to proceed. You put it in this sort of situation, figures out again the right thing to do here. It brakes and merges behind the person, lets the person go through first. All of this makes sense. Eventually, we put it in a situation like this, where what it decided to do is to cut the person off and force them to decelerate at 5 meters per second squared. Because that was, more efficient than not doing that. And so you kind of have to go back to this and say, what's going wrong here? And part of what's going wrong is that you didn't quite maybe get all these trade-offs, all the combination right. Another thing that's pretty fundamental that's actually going wrong is that the reason this is not cool to do, you should only do this if you really need to. And that's because there's part of the objective here that we're completely missing, which is that actually these cars should not be jerks to other people, right? Unless they really need to. And so we ended up kind of adding what we call the courtesy term that cares about the efficiency of other folks. And then here's a four-way stop. Like that fixed those previous problems. Here's a four-way stop. At this four-way stop, the car doesn't go. It doesn't wait there and let the person go. It decides to back up, inch backwards, because that's very courteous to the other person. That was what makes it more likely for the person to proceed faster through the intersection. And I kid you not, we ran this. I'm sweeping a lot of details under the rug here. This was like a whole PhD thesis to get cars to be able to know how they can influence other human behavior and so on. But that's not the point in this talk. This actually worked with people went faster to the intersection, I kid you not. But if you have people behind you or if you have passengers in the car, they're now freaking out because why the heck is the car backing up, right? So you're missing more things in this objective function. You miss things about comfort and interpretability, I don't know, stuff like that. So all things that are hard to write down. And so the promise of optimization and reinforcement learning and AI was that we don't have to tune behavior anymore. I don't have to write rules for how cars should behave, right? I can just set an objective and let the car do the right thing in every single situation that it encounters. That's the promise. And it's true, I don't intervene at the behavior level anymore, and that's great. But man, do I have to spend a lot of time tuning up these reward functions or cost functions for these cars. Yeah?
So somehow people have been doing, we've been doing optimization for a long time. So I'm trying to understand what is the new part in here. When you're an airline and you're trying to do pricing, the same kind of factors kind of appear, somehow.
Somehow we've worked it out.
We've survived.
Yes.
I think there's this, we recognize that this is an iterative process. It's not that you just specify your objective and it's set forever.
That's right. I think the recognition here is that it is an iterative process. Whether in the lab or for any sort of application, we always iterate with the designer, with the expert, on what they actually want the thing to be optimizing for. But none of our methods, none of our theory acknowledge that. And I'll get to that in a second. So I don't think anything drastically new changed. I'm just sharing my experience with my, here's the thing. Maybe cars are a little bit more, it kind of tease out a little bit more of the complexities compared to some maybe standard optimization problems that we tend to test out in labs. But I don't think that there's anything really special here. And in fact, economics has known about this problem for a very long time, right? There's something called Goodhart's law, which is you set a metric and then there's such a thing as over-optimizing that metric, and it no longer becomes a good, useful metric.
Even in controls, right? One of the things where people kind of got disappointed from the optimal control point of view was exactly somehow you need to specify.
That's right. Question over there.
Comparison with optimization, we know how to handle constraints in optimization. If we can put constraints here.
Yeah, so this is kind of a common thing that we think that, well, just put constraints, right? But this walkthrough that I just kind of try to take you through, the car wasn't crashing. It had nothing to do with sort of a safety constraint that I was missing, right? It was about not being able to capture the notion of courtesy, not having thought about it ahead of time, not having thought about comfort ahead of time in a reasonable way and not knowing how to write it down. It's about when you have things like efficiency and comfort, not knowing what the right combination of them is. And it's honestly, if we really want to go there, it's about not, writing a chance constraint and not knowing what the threshold should be, and not really believing that I can set a threshold for that chance constraint that generalizes to all possible environments that the car will see. This is actually my stance. It's that whether it's constraints or not, it doesn't matter. Think of it as ingredients that have to get combined somehow. We don't know the ingredients and we don't know the combination for any complex enough real problems. Have you seen this? Who has seen this? Okay, not everyone. So this is kind of a really cool example that I like to show, it's a boat racing game. And this is an agent trained to race in a game. And as you can see, it's not doing a super good job racing. All the other boats are here actually doing the racing. And what is this doing? This is trained via DeepRL. So you might think, well, there's a bug in the policy. Turns out there's no bug in the policy. What I like to say is that the boat is actually kind of a genius, because what it does is it uncovered this strategy where it's looping and it's collecting these turbo thingies at just the time they appear. And every one of them gives it 1,000 points. And so the reward function was score a number of points in this game. And the boat is doing a great job at that, right? So this is a great example of this over-optimization of an objective that seemed reasonable at first. Points in the game is very reasonable. You don't think you have to say, no, but also win. You think that it comes naturally with this. It's very easy to make assumptions implicitly when you're defining these things and get it wrong in the end. The last point I want to make about this is that once an agent that does optimal control has an objective, it's what I call very stubborn, to use very anthropomorphic terms. I hope Ben will forgive me. It's very stubborn, so to say, about optimizing for that. So here's a robot in my lab. It can move things around from some start to some goal configuration, and it tries to be efficient but also stay far away from obstacles and so on. And now if you put it in my home and it's, I don't know, cleaning something up and it's carrying that mug as part of this task that it's helping me with, maybe I look at it and maybe I think, well, if this mug is keeping it very high up, and so I kind of worry that if it drops it, it might actually break. And so I would like it to kind of keep it lower to the ground. And what I might want to do at this point is I might want to actually physically intervene. I could say stuff, or I could physically intervene and kind of correct the robot, right? Actually physically bring it closer to the table, closer to the ground. And the question is, what does the robot do then? Does it, if I let go, does it kind of continue to be closer to this table? Well, no. The robot is like, oh my God, this disturbance that I was just applied was crazy and it made me be so suboptimal. I'm so glad I get to go back to doing things in the optimal way. And I keep pushing, and the robot's like, I thank God you let go, because I get to actually now do what I think is the optimal thing. And that's not what we want, right? I would like for this robot to take my correction and actually interpret it as information, to realize that somehow, if it was doing the optimal thing and I intervened, and I'm not, the person with a stick that keeps disturbing the robot all the time, there's a difference between actual disturbances and people that you're in their homes, right? When they push you away or away from them, that means something. It means that they're uncomfortable with you being that close to them. When they push you closer to a thing, that means something. And so I think kind of the bottom line is that we sometimes like to pretend that the problem is, here's a state space, here's the actions that the robot can take that influence the state of the world, and there's a reward function that somehow falls from the sky. And all of our job is to figure out how to get the robot to optimize cumulative reward. But I don't think that that's the problem. I think that we might have something to gain by acknowledging that it's not the problem. That's not how it works. How it works is that there's a person who wants something. And what the robot should do is do what that person wants. That's a much harder problem. And because it's a much harder problem, naturally we've been kind of drawing the box around this part, because this part is hard enough, and honestly we still have a long way to go to even just be able to solve this part. But I think we're at a time where we can maybe revisit the whole system and start asking the question, what does it mean to acknowledge that this reward doesn't fall from the sky, but it's actually, I'm in an interaction with a person and I'm trying to do what the person wants me to do. And that's a problem that I've gotten very, very, very excited about lately. I don't have an answer to this kind of problem, but I have some thoughts and a little bit of progress that I figured I'd try to share with you today. Okay, so in a nutshell, I think we shouldn't be trying to optimize specified reward because the specified reward is often wrong. What we should try to do is optimize intended reward. But intended reward is a very nasty thing, right? Because it's in the person's head. And so formally, the way I think about this is I think of it as that there's some parameterization of the reward function. And we're going to call these parameters theta. So they could be, the thresholds on constraints, because I'm being very liberal with what I call a reward function. They could be weights, like I was using for my car, right? Weights, trade-offs between different important things. It could be weights in a neural network that takes somehow the state and action as input and outputs a scalar, any of that, right? So we're going to commit to some parameterization. And by the way, that's an important how the heck do you figure out what the right parameterization is something that I'd like to discuss towards the end. And now the idea is that the robot doesn't get to see theta directly. This is hidden state. And so what it needs to do is actually have some belief over theta, try to estimate it somehow so that it can actually do well with respect to this R theta that the person would like for it to ideally optimize. And if you think about it from this perspective, what we currently, sort of default way we use these systems is, at least from the system's perspective, not what actually happens in real life, is if the designer says, here is a reward function that I'm going to write down, right? And it's theta tilde, and notice that it's not theta, it's theta tilde, right? Because we're not going to get this exactly right, much like I didn't get it right when I was trying to set it up for the cars. So when the person says that, then what we default to as an answer is for the robot to say, OK, well, this is a perfect sensor, right? It gives me perfect information. It completely identifies the reward. And so I'm just going to set the reward to be the thing that you told me to, because you're perfect and you produce the correct thing. And that's the thing that I have a challenge with, right? Because if you think of it from the perspective of there's something that they want, and they can try to extricate that, right? It can try to actually write it down, but they're not going to get it perfectly right. Really, what we're doing is we tend to overlearn from the specified reward. So that's bad. But the good news is that I think actually we're underlearning from a bunch of other sources that are available to these robots, like me pushing on the robot. Right? This is the kind of thing that should provide it information about what I want, but the robot right now by default is just leaving that on the table because I'm somehow some disturbance to it. And I want to sort of clarify that it makes sense that this has been the approach to physical interaction, for instance, because it's not obvious that when people intervene, they're trying to communicate to you about the reward. In fact, oftentimes they're not trying to teach you anything. They're literally just trying to, in the moment, correct what you're doing and make sure that you're doing the task in the right way, right? So when I push the robot away from me, right, I'm not thinking, oh, let me teach this robot about my proxemics preferences. What I'm probably actually thinking, oh, the robot is getting a little too close to me in the moment, so I'll push it away, right? But my claim is that when people do this, yes, you should go away from them, but you should also learn something about how what you were doing was wrong and how maybe they're giving you information about what the right thing to have done would have been. Maybe the most, this is a little crazy, I'll say that in advance, but maybe the most extreme version of this is if the robot is about to do something terrible, like, I don't know, knock something over or enter water, and I know that that's not a good thing for it to do, and the designer hasn't, anticipated ahead of time that telling robots not enter water is something that we should be doing, I might switch the robot off. I might hit the off button, or I might hit the e-stop button, right? And I think that's also well, the robot should stop, and I'm doing this because I want the robot stopped. But again, I'm giving it little bits of information about what it was doing, and at the very least, it should know that whatever it was about to do was disastrous, right? If I ended up hitting the e-stop. My favorite example of this sort of thing about how there is information out there that we're not really necessarily using or taking into account right now is this one. So imagine that you enter a room where there's this beautiful house of cards laid out. And I ask you to clean up the room. but there's this thing in there, right? Are you going to destroy the house of cards? Probably not, right? Probably all of you would clean up, but leave the house of cards as is. How does the robot figure that out, right? So somehow, there's no explicit feedback that I gave you. I haven't really told you anything. I completely left out that you shouldn't be destroying my house of cards. But somehow, the fact that just the mere presence of the house of cards there has told you something about, arguably, what I care about and what I don't care about. So what I've been excited about lately is that while the specified reward doesn't kind of carry as much information as we typically would like to, it turns out that people just can't help themselves but leak information about what they want. And I think that there's kind of this untapped opportunity of being able to read into this information and use it so that our robots can maybe compensate for stuff that we might not be able to think about ahead of time or specify ahead of time quite so well. And so this has been the question for me. It seems like there's a lot of information there in the environment, in human feedback, in human actions. How can we extract it? How can we take that as information and give it to the robot? And maybe I'll actually use the board for this, because the way we've been thinking about this problem recently has been to essentially start with, there are two known ways in which you can actually use human actions, human feedback to learn about the reward function. So there's like kind of two tried and tested ways. And they're not about physical corrections or the house of cards or the e-stop, but they exist, and maybe we can take some inspiration from that and see if we can generalize that to these more nuanced sources of information that we're talking about now. And so those two areas are comparison-based learning of reward functions and inverse reinforcement learning. So we know how to do two things. I'm going to kind of go through them. One thing we know how to do is if we show the person one trajectory psi A and another trajectory psi B, and they pick this one, they tell us this is better, right? So imagine that you have a car and you can showcase to the person two behaviors and ask them, okay, which one do you prefer? This is the kind of thing that people have done before. This we know how to interpret as information about the reward function. So if I draw a quick little environment mock-up example here. So here's an example where I have a grid world, there's a start, there's a goal, there's a bunch of water in the middle. And if I show the person one trajectory psi A and another trajectory, maybe this one, psi B, and they told me psi B is better than psi A, from this I should be able to actually derive that the person doesn't want the robot going over the water. And the way this works is if I have to parameterize the reward function somehow. Maybe I say that our theta of SA is simply theta transpose times features of that trajectory, where features are like, are you over the water? And did you reach the goal? So if I do that, then something very easy that I can do is look at the person preferring psi B to psi A and saying, well, that tells me something about the reward function. In this case, what that tells me is that our theta of psi B is better or equal than our theta of psi A. This is a constraint that I now imposed on what theta could be. And in this little toy example, if I think of this unit circle as the space of thetas, the space of possible weights that I can put on, is the water good or bad? Is the reaching the goal good or bad? Then what this sort of constraint does in this linear case is it produces this hyperplane where it says on the left-hand side, all these thetas satisfy. On the right-hand side, all these thetas don't satisfy this constraint. So if this is sort of the water axis and this is the goal axis, essentially what happens is I'm drawing this, and this person is telling me that none of these are legal. The ones that like water. And I don't learn about the goal in this case because both of them actually end at the goal. So I haven't really gotten any information about the value of that. Another thing we know how to do is inverse reinforcement learning. So in inverse reinforcement learning, roughly speaking, the person gives me a demonstration side D. So they actually show me how they would navigate this in this particular environment. And that too gives me information about what the reward should be. Because it essentially tells me that whatever theta is, r theta of psi d has to be greater or equal than r theta of psi for every psi. So this gives me a lot more information about what feasible rewards might be. And so those are two things we know how to do. Now, the only problem we have now is that when the person corrects the robot or says something to the robot or specifies a reward function for the robot, so actually gives me that theta tilde, right? How do I make sense of that? Because those are not, trajectories that the person is choosing from. And one perspective that we found pretty useful recently has been to say, what if they sort of are? What if you actually think of these actions that people take that are not in the robot's MDP, they're not behaviors that are trajectories in the MDP that the robot is solving. What if you actually think of these as choices that people are making that are rational with respect to the reward function, but somehow need to be translated into behaviors? So what we've been thinking as a generalization of this has been to say, what if we think of all these other pieces of feedback that we're getting as the person making a choice, C star, from some set of options, capital C. And we allow this to be an explicit choice, like it is in comparisons, or an implicit set. So already in inverse reinforcement learning, we've gotten comfortable with the fact that we're not showing the person all possible trajectories and then they're picking one. When they're demonstrating a trajectory, they're implicitly making a choice, as this is the right trajectory, out of this space of all possible trajectories. So they're working already with an implicit set of options. And so maybe that works more generally. Maybe we can say that the person is making a choice C star from some implicit set of choices. Let's take a concrete example. So let's say that the person pushed the off button, and that was their choice. How could I make sense of this? How can I tie it back to the reward function? Where I can say they had options. They could have done that, or maybe they could have done nothing, right? And they chose implicitly, when they chose to turn me off, implicitly they chose to not do nothing, which would have let me continue. So what I would love to do here is I would love to write down something like this, like r theta of C star is greater or equal than r theta of C for every C in capital C. But there's a syntax error here, right? I can't actually apply the reward, which operates cumulative reward on trajectories. I just corrected that. I can evaluate rewards on state action pairs or on cumulative reward on trajectories. I can't evaluate it on the person pushing the off switch or the person saying something or the person giving me a reward function. And so what we can do is sort of borrow a page from natural language and think about a grounding function. That maybe there's a way to take these choices, this choice set, and actually map it onto behaviors for the robot. So something that takes in little c and maps it onto an actual trajectory in my MDP. And so in our example of the person pushing you off, what you can think about is, well, what's the grounding of the person turning me off? Well, that does actually correspond to a behavior. It's the behavior where I was doing whatever I was doing until I almost hit the water, and the person turned me off, and I stopped. And so I stopped for the rest of the time horizon. I stopped doing anything, right? I kind of executed the null action. And what's the grounding of the person doing nothing? Well, it's whatever, and this is an assumption, it's whatever I was going to do, which presumably was to go straight through. Now, the reason I say this is an assumption is because if we interpret humans as making this implicit choice this way with this grounding function, we're assuming that the person sort of intuited what the robot would have actually done. And that's not always the case. They could actually be wrong. It could appear to you that the robot's about to do something super bad when that's not actually the robot's response. So you could get this wrong, and we'll talk about misspecification in a little bit. But that's sort of a framework or a formalism for how to interpret human behavior that we've been finding you can stretch pretty far, surprisingly far. So we saw how it can apply to stuff like this, where now you can, really what we're saying is our theta of the grounding of C star is greater or equal than our theta of the grounding of C for every C. So that's kind of how we resolved this thing into something that actually makes sense and gives me information about the reward function. So this is interesting. What I find more interesting is how this applies when the person actually specifies a reward function. So let's think about that. Let's think about how you can use this notion of the person making a choice, an implicit choice, and apply it to the person they actually specified a theta. They gave you a theta. Let's call that, I don't know where to write anymore. Can I go over there? Is that okay? What the person gave you is theta tilde. Okay? How might we make sense of theta tilde? Not as, well, no, this is actually the definition of theta. How could we possibly interpret it as just information about the reward? So the person specified theta tilde. The first thing that, that formalism sort of, that's kind of a recipe that we can go through. The first part of the recipe is that we need a implicit or explicit set of choices that were available to them, right? So this is potentially all of the possible rewards that they could have specified, but they didn't, right? So any other theta that is in the space in that parameterization, in the space induced by a parameterization. And now the question is, what's the grounding? And this is sort of where...
So they're actually picking a theta in the space. They know all about the parameterization of their...
So you can do it. So we've actually done this, good question. We've done this in two ways. We've done it in the way of there's a fixed parameterization, and they're picking a theta in that parameterization. And so this is what we do for stuff like cars or motion planning for arms that I'll show in a second, where like the person kind of tunes a thing, and it works across a number of environments, but then it breaks in some new environments. And so it's not kind of the definition of what they would actually want the robot to optimize everywhere. Another way we've done it is they actually have access to some interpretable things that they can write down, and that's their space. So this would be like a capital theta prime of the language the designer has access to, for instance, weights on various features. But when you run your inference over the real theta, you run that inference over whatever other more expressive space you want. So you can do it in both ways. There's nothing that constrains you after you have a grounding to write your constraint, our theta of the choice is greater than our theta of other choices. There's nothing that will constrain you from using that same parameterization. So the person could use a simplified parameterization. Well, what's the grounding? Yeah.
Can the human pick a policy of how they will interact? And in that case, how is this mapping? It feels like it won't always map to a single trajectory. It's a policy that they are picking.
Yeah, so this is one thing that I haven't talked about is what happens if, so in IRL, for instance, you could get a full policy for an MDP. It's usually hard for people to pick that, but if you actually parameterize it somehow, then that would be another way that you can say, this is a choice that the person has made. They pick these parameters in the policy, and then you'd have to think about the grounding of that policy. One thing that we haven't talked about yet is how in practice we don't necessarily map to a single trajectory. We can map to policies, or we can map to probability distributions over behavior as well. And the same sort of thing applies because you have reduced it to something you can evaluate reward on. All that you need is a grounding that reduces it to something that's behavior in robots MDP, so we can evaluate reward on that. And in fact, when the person chooses a policy from, if you reduce the parameters, so you say, here's three parameters that you can set to tweak a policy, kind of like what Emma was talking about, right? There's like known things, known decision points. And then you can tweak those parameters. What you could do is actually realize that that's not the optimal policy that they chose, but it's just the optimal relative to the set of choices they actually had. And when you run your inference, you can run it on an inference on a space of reward functions that's much more expressive, but use that as a constraint as opposed to the definition of the optimal policy. So when you come back to the person specified a reward function, what we found really helpful as a grounding is actually to say that the grounding of a specified reward, theta, is actually the behavior that's optimal with respect to that reward, but in the environments that the person has actually looked at, as opposed to all possible environments. So let me say that again. The default thing that you would do is you would say, this is the definition of the reward function. It's better than all other rewards everywhere. By using this grounding, you're saying a reward function is really just behavior that reward function induces. And instead of assuming that behavior is the right behavior everywhere, in every new situation that the robot would ever encounter, you're limiting that. You're kind of putting it in the context of the training environments that the person has actually used when they designed the reward function. So this is really just, if you have one environment, to simplify, this is all the person has told you when they specify theta, say theta tilde, is that this behavior is good relative to what? Compared to behavior induced by other reward functions that they could have specified. Or if it's policies, to your example, right?
The theta are the parameters of the reward function, right?
Yeah.
So they're telling you that. So why are you saying that they're giving you the reward?
If they're giving you the parameters of the reward, then they're giving you the reward.
Function.
Yeah.
They're just telling you that they're okay.
Yeah. So
No, they're not giving you the reward of anything that.
they're not giving you the reward evaluation. They're giving you the cost function, right? And so that's been an interesting sort of shift for me, because obviously I used to think of if the person specifies a cost function, then that's the cost function I should optimize everywhere. But the realization is that people tweak these things until they work on the set of environments they're actually thinking about. And you have no guarantee that when you optimize that same cost function that they defined, that will produce the desired behavior on any new situation your robot will see out there. And so by essentially taking the cost function and saying, no, this is really just evidence about the reward, and the way I can interpret it is I can say the person looked at a bunch of cost functions, they looked at a bunch of environments, they chose the cost function that produced the behavior that they liked on those environments, and that's all that I'm allowed to assume about this cost function. Then you're kind of taking a step back from what was specified and producing this sort of whole family of reward functions that are consistent with that. Yeah?
So you're kind of enlarging the model that you have, because you were writing this RT of psi, and maybe this is going to have a second parameter, which is like what environments.
That's right. When you optimize this, it has to be in some, let's call it train or test or development, which is, that's the behavior, not in every possible environment. but that's the behavior in the environment that they actually looked at. And if you have multiple environments, that's just the same as having multiple demonstrations in inverse reinforcement learning. Yeah?
Can you say more about how you get the scope there? About how, I mean, so the whole point of having an optimization going on is because you don't want to look at every environment, right?
That's right. And so that's sort of the cool thing, is that there might be a bazillion environments that you'd like the card to work in. And what you really do in practice is you form for yourself what you think is a representative set, right? So in motion planning, what do I do? And maybe I can actually show you some of that. We'll go back to this. So here's motion planning. I have a robot that moves around a person. What do I care about in motion planning? Well, I care about the robot not hitting stuff, but if there's fragile stuff, I want to stay further away from it. If there's a person there, I want to stay far away from the person as well. Maybe there's proxemics preferences where I want to stay, further away from their head than their shoulder and stuff like that. And so one thing that you do when you want to define this cost function for your arm for motion planning is you'll create a bunch of environments. You position things in various ways, and then you run your trajectory optimizer, and you see whether it produces a good behavior that you actually like, right? And so let's say you pick 20 environments, and you ran your trajectory optimizer over that, and you tweak and you tweak and you tweak and you add to your cost function until the behavior that you see is the right behavior in all of these 20 environments. What we've been finding is that you can do this, and then you can take another 20 environments at test time, and the robot will, when it optimizes that same cost function, will do the right thing in all of them. And then there's going to be a 21st where the robot does something really stupid. That is optimal. I mean, assuming that you don't have problems with local optima and so on, right? That is optimal according to what you specified, but it's not what you want. This is sort of the pattern that we keep seeing, and with the car as well. This happens over and over again. So how do you get that context? It's literally the environments that the person has tested the reward function on. Yeah?
I'm curious about the conceptual distinction from learning from demonstrations, because the demonstration is always in the context of a given environment. Right?
Mm-hmm.
How do you see?
So I guess the claim is that a healthy way to look at specified cost functions is also in the context of given environments. So the goal that we have in both inverse reinforcement learning, when we look at demonstrations, and in this stuff, is the goal is the same, which is I'd like to extract a cost function that actually will generalize to every new environment that I'll see. And what breaks with cost functions is that we tend to say that if they work on the 20 environments, then they will generalize everywhere, but they won't. And so sort of all that we're really saying is, look at them as providing you information about the reward function, the cost function, not the definition. And then the question is, well, how did they provide you information about it? Like, what's the observation model there, right? How do you relate the cost function that was specified to the cost function that you should be optimizing? And so...
I guess the step now is so all of these are put on some kind of query model into this global reward function. Essentially turning everything into now everything is now this weird banded optimization over reward functions. So that we do something on the outer loop now?
So you're gonna hold a belief, which we haven't talked about the probabilistic stuff. For now, it's just a feasible set. And the key here is every time the person does something, right, like turns you off or tells you what the reward function is, theta tilde, or corrects you, or whatever it is that they're doing, that counts as additional constraints, additional information you're getting about this underlying reward function that is the one that the person would like you to optimize everywhere. And we're making the assumption that is sort of sketchy, that there is a reward function that the person would like you to optimize everywhere that is in your parameterization, that you have access to some theta, right? So we'll revisit that hopefully in 10 minutes, right? But that, I think that's the sketchy part. The sketchy part is that, because if that's a neural net, then you need a lot of data, a lot of information. And if you say, well, there's these features, and we're doodling with how these features combine, then you might have missed something that the person actually cares about. So that's sort of the challenge. But yes, you have a space, and instead of taking what the person said and say, well, that's the definition, you're now looking at all of this information that they're giving you, including this cost function that they specify, and saying it's just information about what I should really be doing. And what we're showing here is that you can take inverse reinforcement learning and kind of extract from it one key principle, which is that the person is making a choice that is rational with respect to the reward function from this implicit set of options. And finding that remarkably, you can look at a lot of these different behaviors as rational choices with respect to their reward function from a set of implicit options. And you have to, the work that you still have to do in order for your robot to have the capability of interpreting all this is you have to define this implicit set of options for every new feedback type you're considering, and you have to define the grounding function. But it turns out you can do this for a lot of different types of feedback, and it kind of works. So you can do this for the off thing. You can do this for the reward function. And here's what it does. So this is, a very simple motion planning thing, different weights, different things. And this is the kind of process you typically go through. You have these features, and you keep on tuning things. And here we're showing linear combinations. And you keep tuning things until the robot does the thing you want everywhere. And then you declare success, assuming that that's the reward function that the robot can optimize in every new situation. Here's one environment. This is the trajectory that the robot comes up with when it optimizes what you specified. This worked very well. Here's a new environment. And the robot just decides this is the optimal thing to do. Now, could I have fixed that with hard constraints? Yes, in this case, I could have totally fixed that with hard constraints, but it would have broken in some other way. And I don't know what's different about this environment. It doesn't look necessarily very different from training environments. I don't know what I missed, but I missed something. And so what we're really saying is that instead of the robot doing this optimization, the robot should look back at the environments that the person actually checked the reward function for and said, yes, this works. I've gotten it to work on all of these. And update its belief about what the actual weights are. So here theta is just these weights on these different features that we were tuning over there. So in this case, even the space that the programmer is working on and the space that we're doing inference in are one and the same. And it's using that model to say, okay, the extent to which a thing is probable to be specified, if this is the true thing, is that it induces good behavior with respect to the true thing in these environments. Not everywhere, just in these environments. That's all that I'm really allowed to derive from. Now, I threw in a probability distribution there, and I just wanted to make the quick point that we talked about constraints, like when you evaluate the reward on the grounding of the choice, it has to be higher or equal than when you evaluate the reward on the grounding of any other choice that the person could have made but didn't. In practice, this assumes that people are just perfect little optimizers. You'll give them choices, or they'll implicitly think of choices, and they'll pick the correct one, the one that's best with respect to the reward function, and that is not how people work. Usually we work with a model that looks more like this, where we talk about the probability of a choice C star under the correct theta, and under the set of choices capital C, as being proportional, well, let me actually write it fully, as being equal to the exponent of some rationality or temperature coefficient beta times the reward under theta of the grounding of that choice that they actually chose, divided by the sum. You normalize this over all possible choices. You say, well, that's e to the beta r theta of the grounding of C. And so what this does, it's a fuzzy version of this. When you take beta to infinity, you're getting this. when you take beta to 0, the person is choosing randomly. So it allows you to kind of capture some noise in the human's choice. This comes from, this kind of a progression, if you want to know the history of this, right? So in the 40s, economists were like, people are maximizing utility. They're picking the choice that has maximum utility. And then Luce and Shepard in the late 50s said, no, it's actually a little noisy. And that's still wrong, by the way, and we hopefully get to chat a little bit about that. That's still wrong, but it's usually a much more robust assumption to make than assuming that what the person picked is the optimal thing. And it's the same in IRL and all of that. And so that's why I threw in a probability distribution here, because I don't want to assume that people pick, the thing that is perfect for these 20 environments that they looked at. I want to allow for a little bit of noise on their side. And when you do this belief update, which, by the way, theta is usually high dimensional and continuous, and we can't actually run this, so we do some MCMC, and some stuff gets lost in that. But when we ran it in this situation and planned in expectation over this posterior distribution, we saw sort of fairly consistently that the robot had the behavior as much closer to actually what we wanted it to have. In this case, for instance, sort of hedges its bets more. To understand that, I think maybe this visualization here could be helpful. So here what we try to show is for different types of feedback, comparisons, demonstrations, the person corrects you. So they give you this, in this case, they give you this external torque that perturbs your trajectory. They might, tell you to stop. They might speak to you and tell you to avoid the water, or they might actually set a reward function. Might tell you this is the trade-off between avoiding the water and reaching the goal. These are sort of the groundings, right? So the grounding for comparisons and demonstrations are just the identity, because those are already behaviors. They're already trajectories. The grounding for stop is what we talked about. The robot goes and then stops and compares that to having continued. The groundings, grounding for avoid water. The grounding for this proxy reward, these are all trajectories that are optimal in respect to that proxy reward. And that speaks to the fact that you can have a distribution over trajectories, not necessarily a single one. And this is the effect on the reward function when you use the constraint formulation. Whoops, not the noisy formulation. So the comparison just cuts the space in half. The demonstration is more informative, right? But just getting one demonstration in one environment doesn't completely tell you what the reward function is. And what I find interesting is here, right? The proxy reward, even though I specified a reward function, there are many other reward functions for which that behavior that this produces is good behavior. And that tends to happen. So kind of back to Andreas's point, and I think your point, right? I pick 20 environments that I think are representative. I define a reward function that works well for all of them. Cool. But the power in this is that there might be a lot of other reward functions in the space that actually agree with this one that I specified on these 20 and start disagreeing later in other environments. This technique, what we found is so kind of magical about, the thing that got me excited about it, is that you hold this distribution, and in new situations, you can see them starting to fight. And you can plan an expectation. You could do risk-averse stuff where you hedge your bets and say, OK, I want to be good with respect to any of these probable reward functions. Or you can throw a flag and say, you've told me to do blah, but I think you might have meant this other thing, and now these two behaviors are actually different in this environment. What's up with that? And I found this to be very, very powerful, because it's essentially kind of telling the robot that there's something there that where it doesn't know how to do. There's something that it doesn't understand. So I'm sort of out of time. I will very quickly, I'll skip this. I'll skip that. That's a user study. Very quickly to say that in corrections, which is what we saw before. Now, whoops, that's not the right video. Let me skip over some things, skip over some things, skip over some things. That's how we do corrections. It's applying the same formalism. I push on it, and now the robot uses that external torque that I applied, translated, grounded into a deformed trajectory, uses that deformed trajectory to say, you've made a choice that this trajectory is better than whatever I was doing, and then derives what, again, linear cost function, so what ways to make sense that explain that. So interprets it, again, as evidence about the reward. I like, just to show that this is not something that works with just me as the end user. Here the robot wasn't keeping the cup upright, and we asked people to correct that. And so you can just see on the left, the robot just running kind of a state-of-the-art PHRI thing, which is to just run impedance control to be somewhat compliant to the person. But then when they let go, you kind of go back to tracking the original trajectory.
How can robots tell the difference between an obstacle and an impedance?
Vision. Yeah. So this is a good point, right? So I've sort of said in the beginning that, look, when I push on the robot, it means something. But then there are also people poking robots with sticks, right? So how can you tell the difference? It's, it has to be the context you have somehow. And I think that is indeed hard. It's a challenge for interpreting these things, right?
Can that be pattern and correlation?
What do you mean?
So, for example, the car example. If someone's driving a car in the city, they're just driving, or someone drifting with a car, the purposes are completely different. But can the car distinguish the difference by pattern, seeing, being trained by the pattern and the correlations that it has, so it can learn that this guy is drifting or...
Maybe. I worry a little bit about correlation. My preferred mode of operation there would be to do actually active learning, to do active info gathering. So for instance, we thought about things where people push on the robot. There might be many things that explain what's going on, in the robot might, can now the robot control in such a way that it maximizes expected info gain or something like that. So when you know that people can intervene and correct, can you seek informative corrections that try to disambiguate between what happens? The very last thing, whoops. The very last thing is this house of cards thing, and I don't have time to go into this, so I'll just quickly mention that for this one too, what we've said is when you walk into an environment, you get to see the state of the environment, but people, even though you haven't been privy to see that, people have been actually acting in that environment. The reason you can tell that this is important is because the only thing that explains this didn't magically appear. Someone had to actually build it and put effort into it. The reason you walk in, a very stupid example, you walk into a room and there's a vase in the middle that's not, damaged, that's still there, right? How can you tell that you shouldn't damage the vase? Well, if you think about all the different states the world could have ended up in, the world could have easily ended up with broken vases if people didn't actually care about avoiding the vase. And so one thing that we've done is we've said that the state of the environment at the initial time is a choice that people make. The environment could have been in many other states. And what's the grounding of a state as a choice that people make? Well, it's all the possible trajectories from the actual beginning of time until that state that actually end in that state. So this is, the person, we don't know where they started in a room or whatever, but all the possible way they could have walked, right, through that room that end up at this state in which the vase is intact. And then there's all the other behaviors where they would have broken the vase. And those are not consistent with what you're seeing. So you can think of the vase as a choice where the grounding of a particular state is really the trajectories that the set of trajectories from, I don't know, negative t to 0, such that psi of 0 is equal to S0. That's what you ground it in. You ground it in behaviors. And no behavior that crashes into the vase is a behavior that leaves the vase intact. And so that's how you can figure out that people care about. You need to know a lot of things. You need to know that vases break when you go through them. You need to know a lot of things. You need to actually have access to dynamics for everything that I've talked about today. But that's how you know. That's how you can take information from the state of the environment and leverage the fact that people have been acting already in the environment according to their preferences, noisily rational, so not 100% according to their preferences, and gain information about what their preferences could have been. And so we get stuff like, the robot, you telling the robot to go to a door and the robot avoiding the vase, and it's really cute. We also get stuff where there's a train that runs in the middle of the room that needs batteries, and it's still running. So what does the fact that it's still running tell you? Well, it's only consistent with behaviors where the person actually fed batteries into it. And so the robot that optimizes not just for what the person specified, but uses this method to figure out what the implicit preferences in the environment might be, goes and not just exits the room, but first puts batteries in the train and then exits the room. It's very cute. But it's all grid worlds, because that inference is really hard to do and more than grid worlds. In general, these inferences, right, are very tricky. We use a lot of sampling. And sometimes that works, sometimes that doesn't. When we try to use neural nets as the representation of the reward function, that computational problem gets worse. But maybe we can deal with that. I think what gets really bad is that there are so many possible reward functions that agree with the data that you have. And I don't know how to impose a prior on reward functions, how to regularize them, or what the right inductive bias in the space of reward functions is. And it seems like we need that in order to capture all the things that the person completely forgot about, like how I forgot about user comfort or something like that. Right? You're not going to get user comfort to be invented by this unless you run the inference in an expressive space. And I should say, you're never going to get user comfort to come up as the person cares about this when you don't have any information about it. But what you're going to get is you don't know whether comfort matters or not, because optimizing for comfort produces this or not, produces the same behavior in those 20 environments that you looked at. And based on that, you can figure out that you don't know about these different things that the person hasn't really thought about, because they all just produce the same behavior. That's sort of the big thing that works here. It's not, you're never going to figure out that something is important or not. You do need to close the loop and go back to the person and say, here's an environment where these things disagree. Tell me here's what you told me to do. Here's the thing that optimizes for comfort. Which one is better? And then the person can tell you. But yeah. Okay. I think that's basically it. The message, because we're 3 minutes over, the takeaway for me is, whoops, never mind. The takeaway for me is that this is the full problem, and I don't know how to solve that full problem, but one realization that we've had is that when people specify stuff, take it as information about what they want. When people do all sorts of other things, take it as information about what they want. And that maybe this is a recipe that works for surprisingly many different sources of information. I don't know what new is out there and if they'll fit in this or not. But it feels like we're taking an epsilon step towards actually accessing more and more about where the reward function comes from. And these are the people involved who actually did the work. So thank you.